Hey guys, we've been spending a lot of time talking about trig functions in terms of their graphs, evaluating them, and now we're going to talk about inverse trig functions. Okay, so inverse trig functions of sine, cosine, and tangent. We're going to focus specifically today on their domain and ranges and how we can evaluate them or compose them. So let's answer three important questions first. One, in order for a function to have an inverse, what property must it have? Two, what is our test to determine if a function has an inverse, and why does this test work? And three, does the sine function pass this test? So go ahead and put me on pause. You should be able to answer these three. All right, so we know that a function must be one-to-one in order to have an inverse. We use the horizontal line test to test for this to make sure that every input has exactly one output, and that the sine function and that every output has exactly one input. And the sine function does not pass this test. We can even see that from our graph here. Think about our horizontal line test. If I put a horizontal line in here, right, it crosses more than once, so that would not work. Okay, let's get rid of this now. So now let's answer a new question. What did we do if a function was not one-to-one, such as the sine curve? Do we just give up? Of course not. We persevere. That's the key word of this unit. We persevere through the tough things. So what can we do? Well, we know that when we want to restrict the domain, that we want to cover the entire range in order for it to be one-to-one. So if I want to restrict the domain here on the sine curve, I'm going to use yellow. If I want to restrict this domain, I could go from negative pi halves to pi halves. Again, why would I choose it here? Because I want to cover the entire range from -1 to 1 in order for it to be one-to-one. So what is the range of y equals sine of x on this restricted domain? -1 to 1. How do we solve for a function's inverse algebraically? Well, we know already that we would switch x and y and then solve for y. All right, that's how we would algebraically solve for an inverse. And we can do the same thing with y equals sine of x. If we switch x and y and solve for y, we would get y equals inverse sine of x. Okay, but then think about what happens to that domain and range. What's the relationship between the domain and range of a function and its inverse? Oh my goodness. They switch. Which reminds me of the song by Will Smith. Switch, switch. If you don't know what I'm talking about, then that was embarrassing. But if you think about this, so what is the domain and range for this inverse? Well, think about what the range was before. Well, the range before was -1 to 1, so now that's my new domain. And my domain before was negative pi halves to pi halves, so that's my new range. So the domain and range switch. Okay, so how should we restrict the domain of cosine so the function is one-to-one? Go ahead, put me on pause. Let's see if you can get this. All right, so our domain is from 0 to, I don't know why that says infinity. I think I'm losing my head. 0 to pi, okay? So from 0, this is pi here. Pi should be included though. Our range is going to be from -1 to 1, which, by the way, means that the domain and range of cosine is actually reverse of this, but we'll talk about that shortly. For tangent, same thing. Go ahead and see if you guys can come up with a restricted domain here. Okay, so remember, because we have these asymptotes here, these vertical asymptotes at negative pi halves to pi halves, to get our restricted domain, we would go from negative pi halves to pi halves, not included because of the asymptotes. Our range is from -infinity to infinity. So let's talk a little bit about notation here. So we do have two different types of notations for inverses. You might see the inverse of sine looking like y equals sine to negative first x, although we would never say that. We would say inverse sine or sine inverse of x, which is the same thing as the arc sine of x. Same thing for cosine. Inverse cosine or arc cosine, inverse tangent or arc tangent. Those are all the same. They mean the same thing, just two different notations. Okay. Input and outputs here. Think about, you don't have this in your notes, which is fine. If I had y equals the cosine of x, think about what we used to input for x. I might do cosine of 30 degrees, or I might do cosine of pi halves, or something like that. I know that those are different. But our input here were angles, right? Whether those angles were in radians or degrees. And what was our output? Our output was the ratio of sides of the triangle. Think about, when we drew the triangle, then you had to determine opposite over hypotenuse or whatever it happens to be. That's a ratio. Now, when we're talking about inverse, we actually reverse that. Now our input is going to be the ratio of sides, and our output is going to be angles. Notice that these are in radians here. Okay, and these should make sense. We just talked about what the domain and range for sine, cosine, and tangent were, so they're switched. All right, so now let's practice some problems here. These ones we should know how to do. We spent some time solving what's the tangent of theta, and theta could be between 0 and 2 pi. And then we also want to evaluate these inverses, arctangent of 1. So just to do the first one with you guys, if I was doing tangent of theta equals 1, I know that theta could be pi over 4, or theta could be 5 pi over 4. Both of those are between 0 and 2 pi. Now, let's think about this. This gets a little bit different. For arctangent of 1, what this is saying is at which angle does the tangent equal 1? But also we have to go back and think about, okay, well, what's my domain for tangent and what's my range? Well, 1 is in my domain, so that works. My range is from negative pi over 2 to pi over 2. So that being said, this is going to be pi over 4. Why not 5 pi over 4? Remember, this domain goes from negative pi over 2 to pi over 2. 5 pi over 4 is not in that range. Sorry, I think I said domain a second ago. All right, let's have you guys try these 4. Go ahead and put me on pause. All right, so let's take a look here. For cosine of theta equals 1/2, we know that that could be 2 pi over 3 or 4 pi over 3. But for the inverse cosine of negative 1/2, to think about my range. My range is from 0 to pi, which the only one of these that fits in that range is 2 pi over 3. Okay, next, sine of theta, we could get equals negative root 3 over 2. Theta is 4 pi over 3 or 5 pi over 3. For the arc sine, now think about our range for the arc sine. That's from negative pi over 2 to pi over 2. Neither of these are within that range. Where does this come from? Well, pi over 3 is coterminal to 5 pi. Negative pi over 3 is coterminal to 5 pi over 3. So we can play around with coterminal angles. Okay, let's try this one. Oh, I forgot to ask you guys an important question though. Explain why these values are different. Go ahead, put me on pause. Okay, so let's evaluate the secant of the arctangent of negative root 3. Let's see if you guys can figure this out first. Since this is a composition, I would start inside and work outwards. Go ahead and put me on pause. All right, so I started by finding what's the arctangent of negative root 3, which, just to double check, is negative root 3 in the domain of arctangent? Yes, because the domain of arctangent is all real numbers. So that is negative pi over 3. See your range. And then the secant of negative pi over 3 is 2. Next one. And the cosecant of the arctangent of negative 5/12. Now, just a hint for you guys, negative 5/12 is not on the unit circle. So what are we going to have to draw? It rhymes with triangle. Okay. So go ahead, try this one, and let's see how you did. Okay, so the key thing here is to really use what's inside here to figure out what my triangle looks like. The arctangent of negative 5/12. Okay, so I know that tangent is opposite over adjacent, so that helped me figure that out. But you might be wondering, how did I know that it was in the fourth quadrant? Well, let's think about it. Since our input is negative, we're going to have a negative angle. And so also it's in the fourth quadrant. Okay, so we have cosecant of theta of this angle is going to be negative 13 over 5. Next example, we want to write theta as a function of x. Go ahead and try this one. All right, so I set this up as a normal trig equation. Cosine of theta is 4 over x adjacent over hypotenuse. But to solve for theta as a function of x, I use inverse cosine. So theta is inverse cosine of 4 over x. Last example. Woo! All right, run an algebraic expression that is equivalent to the expression sine of arctangent of x. Okay, so my hint to you is to draw a triangle again. And my other hint is this is the same thing as x over 1. Go ahead and try. Okay, so the key here is thinking about this being arctangent of x equaling theta. So if we have theta, and I gave you a hint, think of this as x over 1. Well, tangent is going to be opposite over adjacent. So x and 1 here. Oops. I can use my Pythagorean theorem to figure out this third side. So therefore, the sine of that angle is going to be x over root x squared plus 1. Do not rationalize this denominator, especially because it has variables. I mean, if it had numbers in it, it wouldn't matter to me quite as much, but because it has variables in the denominator, do not rationalize it. Awesome. So in conclusion, just remember that the input of a trig function is an angle and the output is a ratio. The input of the inverse trig function is a ratio and the output is an angle. Domain and range only apply if the original problem has the arc inverse function in it. And make sure that you guys understand these, not memorize, understand. All right, very good. Bye.